All right, here we go. The moment you've been waiting for. What are we doing with all of these buckets? We've got all this NADH, we've got this FADH2. What's the point? All right, let's focus on the inner membrane of the mitochondrion. You have your inner membrane, you have your outer membrane, you have this space in between called the intermembrane space. I want to zoom in on the inner membrane and focus on these 4 protein complexes. These protein complexes are going to take these high energy electrons away from NADH and away from FADH2, and they're going to transfer them from one complex to the next. Okay, so what that looks like is this. You've got NADH with its high energy electrons. Now remember, NAD plus was the thing that was oxidizing everything else to turn into NADH. Well, now it's NADH's turn to be oxidized. Now, NADH is going to have its electrons stolen from it by complex 1. So complex 1 rips those electrons away. It's also going to rip the hydrogen away. And this is going to turn back into NAD+, right? So it goes off over here, and it is regenerated back into NAD+. Now, the electron is moved from complex 1 to 2 to 3 to 4. It's transferred from one complex to the next. And as it's transferred from one complex to the next, it's going to lose a little bit of energy, a little pop of energy, anytime it moves from one complex to the next. This is important because what these protein complexes do as they transfer the electron is they take that energy and they actually use it to pump hydrogen ions against the concentration gradient. Now, the hydrogen is coming from all of that oxidation that happened in glycolysis and in the pyruvate oxidation and in the citric acid cycle. Because remember, anytime oxidation occurred, you had electrons being removed, but hydrogen followed. So this is what the fate of the hydrogen is. Its fate is to be pumped into the intermembrane space. Now, I said pumped, so that tells you that the hydrogen ion concentration is already really high in the intermembrane space. So in order to move more hydrogen ions into the intermembrane space, we need some source of energy. Now, normally when we talk about pumps, we talk about primary active transport, which uses ATP. We talk about secondary active transport, which uses the concentration gradient of something else to actively transport something else. But in this case, the active transport, the fuel for the active transport is coming from the electron. It's not coming from ATP. It's not coming from some pre-existing ion gradient. It's coming from the energy that the electron is losing as it moves from one complex to the next. I don't think complex 2 technically pumps protons, but all of these complexes, I think with the exception of complex 2, are going to use the energy of the electrons to pump hydrogen ions against their concentration gradient. Now, here's where oxygen comes in. Oxygen is sitting at the bottom of this transport chain to grab the electron from complex 4. It cleans the chain out. It's like a plumber that just cleans the tubing out. Because if that electron was not removed from complex 4, the chain could become clogged. And that's bad. Just like it's bad when your plumbing becomes clogged, it's bad if the electron transport chain becomes clogged. And we'll talk about why that's bad if that's not clear in another video. But the point that I want to make in this video is that NADH and FADH2, I think FADH2 actually drops its electrons off at complex 2, so it starts a little bit lower in the chain. But the point is that these electrons are deposited into this complex, and as the electrons move down the complex, it's like a slinky that falls down a flight of stairs, right? As the electrons move from one complex to the next, you can think of it as like a little explosion of energy being released as the electron loses chemical potential energy. Now remember, when you take electrons in methane and they fall into the nucleus of oxygen to make water, that's a really explosive reaction. There's a lot of energy being released from that. So the point of the electron transport chain is, instead of letting the electron fall dramatically all at once, the electron kind of stumbles down its energy potential. It's like somebody who trips down a flight of stairs, right? They just bump down the flight of stairs. I don't want to fall downstairs, but I would rather bump downstairs than be like drop 20 feet, right? So you're letting the electron lose little bitty packets of energy, and these packets of energy are captured by these protein complexes to pump hydrogen ions into the intermembrane space. Now, since we're talking about hydrogen ions, we can actually talk about pH. The job of the electron transport chain is to create an acidic intermembrane space. The pH is going to be very low because there are a lot of hydrogen ions in the intermembrane space, and pH is just a measure of the hydrogen ion concentration. So we can say that the pH of the intermembrane space is low. The pH of the mitochondrial matrix relative to the intermembrane space is high, which is just another way of saying that the hydrogen ion concentration is low. So where do the hydrogen ions want to go? Look at this picture and see if you can figure out, where do the hydrogen ions want to go? We're going to talk about where they go in the next video, and we're going to talk about how the mitochondrion uses this gradient to do work.